Okay, so we have seen the Jackknife estimator of bias. We have seen the intuition behind this estimator. Now let's see what is the Jackknife estimator for the standard error of theta hat. The standard error of an estimator theta hat is given by SE of theta hat, which is the square root of the expectation of the square deviation between theta hat and its expectation. The jackknife may also be used to estimate this, and the formula is denoted in blue over here. The jackknife standard error estimate for theta hat is given by the square root of n minus 1 divided by n times the sum of the square deviations between the leave one out estimators and theta hat bar, which is the mean, the sample mean of these guys. Let's look at an example for this, which concerns the estimator for the correlation between two variables. So this estimator is something we are already quite familiar with, which is the Pearson correlation coefficient. And we're going to use this example to illustrate the estimation of both the standard error and the bias using Jackknife for the Pearson correlation coefficient. For this example, we will conduct a mini Monte Carlo study or a mini simulation study. We're going to use this small Monte Carlo study to evaluate how well the jackknife bias and standard error estimates can recover the true bias and standard error of the correlation estimator, Pearson correlation coefficient. So instead of using the analytic solutions for the bias and the standard error of Rxy, the Pearson correlation coefficient, we are going to approximate the true bias and standard error using Monte Carlo inference. So if you recall from a few weeks ago, we can use Monte Carlo studies to estimate the bias and standard error for certain estimators. And these estimates using Monte Carlo studies can approximate the true sampling distribution of our estimator. So the resulting bias and standard errors are unbiased and asymptotically consistent. Also note that the Pearson correlation coefficient is usually denoted by Rxy. This is an estimator for the true rho, the true correlation between x and y. So here we are going to denote the Pearson correlation coefficient instead by rho hat. And we are using this notation just to express that this is an estimator for the true rho. And we're interested in the bias and the standard error of rho hat. And we'll use Jackknife to estimate its bias and standard error. For simplicity, let's assume that x1 and x2 follows the two-dimensional multivariate normal distribution with means of 0 and marginal variances of 1. Further assume that the true correlation between x1 and x2 is equal to 0.5. We're going to do a total of 10,000 Monte Carlo replications. In each replication, we will generate a sample of size 10 for the x1, x2s. We will compute the Pearson correlation coefficient, which is rho hat, our estimator for rho. And we will also obtain the jackknife estimates for the bias and the SE of the Pearson correlation coefficient for that replication. Across the 10,000 replications, we will also calculate the Monte Carlo estimate of bias and SE. So this is essentially the same as what we did when we did Monte Carlo inference for bias and standard error estimation. We know that across the 10,000 replications, the Monte Carlo estimates of bias and SE will be unbiased and asymptotically consistent. So they can approximate the true bias and the standard error. To generate our x's, we will use the MVT norm package and the RMV norm function inside. This is just a code of saying our sample size for each replication is equal to 10. The covariance matrix is this guy, the mean vector is this guy, and we will do a total of 10,000 replications. Here's the code for obtaining the results. For each of the m equals 10,000 replications, we will first sample our x's from the multivariate normal distribution with mean 0 and sigma given by the covariance matrix. The theta hat, which is the Pearson correlation rho hat, computed with the entire sample of 10 observations, will be the correlation between the first and second columns of our samples. The Jackknife leave one out estimates, which we denote by theta hat I over here, will be the correlation computed with the I've sample left out. So for each I between 1 through n, this is the correlation between the first column of x, leaving out the I've entry, and the second column of x, leaving out the I've entry. Then we can apply the formulas for bias and SE estimation for jackknives. The jackknife bias estimate is given by n-1 times the mean of the theta hat i's. So the mean of this is essentially the theta hat bar minus theta hat computed with the entire 10 samples. The standard error is given by the square root of n-1 divided by n times the sum of those things, which essentially is n-1 times the mean of the individual theta hat i's minus the theta hat bar squared. So there's a square that's getting outside of the screen over here, but you should be able to find it in the code for the examples. We are using something called the replicate function over here. And for previous homeworks, you might have seen this replicate function in the textbook. This essentially replaces the for loop from I through m, so I from 1 through 10,000. So essentially, we are going to replicate this thing that's wrapped inside the expressions, so expr, for a total of m times, m equals 10,000. And in the end, for each of the replications, we want to return the theta hat, which is the estimator computed with the entire sample. We will need that to get the Monte Carlo estimates of the bias and the standard error. The bias, the jackknife bias estimate, that's the bias jack, and the jackknife standard error estimate, SE jack. So for each replication, we return these three things. So in the code above, we have omitted for loops. And we did this in two ways. The first thing is that instead of doing a for loop to compute the theta hat i's, which are the leave one out theta estimators, or the rho estimators, we use the supply function. So we are going to, for I from 1 through n, return the following thing. So we're going to return the correlation between the first and second columns with the I've entry left out. This is essentially the same as from for I from 1 to n, we compute this thing and record that inside a length n vector. So this supply 1 through n function something 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 computes the jackknife or the leave one out theta hat i's. This is essentially the same as looping over 1 through n to compute the correlation with the ith observation omitted. The other place where we got rid of the for loop is for the replications, the 10,000 Monte Carlo replications. So we use the replicate function for where we replicate a total of m times. We replicate this expression over here. So this replaces the usual for loop over m Monte Carlo replications. The output of the expression, so the last line, return this vector of theta hat, bias jack, and SE jack. For each of the m replications will be returned by the replicate function. And this will be returned as a matrix. So recall that we call the output of this results. If you check the dimension of results, you'll be able to see that this is a matrix with 3 rows and 10,000 columns. Each row will correspond to each of these guys. So theta hat, jackknife bias, and jackknife SE estimates. Each column will correspond to one of the m replications. Let's give the row names so that we know what they are. So now let's look at the results and compare the Monte Carlo bias and SE with the jackknife estimates for the bias and SE. Let's first look at the approximation of the true values for bias and SE. And these are given by the Monte Carlo estimates, bias rho hat and SE of rho hat. Let's recall that from week 5 and 6 lectures, the bias is essentially the average over the 10,000 replications for rho hat minus true rho. We know that true rho is equal to 0.5. So the Monte Carlo approximation of the bias is given by the mean of the first row of the results matrix, that's our theta hats, minus the true value of 0.5. And this gives us something around negative 0.018, so something around negative 0.02. The standard error estimate using Monte Carlo studies is essentially the standard deviation of our theta hats. So that's just the SD of the first row of the results matrix, and that gives us something around 0.26. Can the jackknife bias and SE estimates accurately recover these things? Well, let's see this. Now, the expectation of the jackknife bias and SE estimators can be approximated by the sample mean over the 10,000 replications. So in other words, to see the expectation of the jackknife bias estimate and the jackknife SE estimate, we can use the sample mean of the bias and SE estimates over the 10,000 replications. The bias will be given by the sample mean of the jackknife bias estimates across the 10,000 replications, which is the second row of the results matrix. And that gives us something around negative 0.025, which is quite close to the Monte Carlo estimate of 0.018, negative 0.018. The standard error, the expectation of the standard error, jackknife standard error estimate, which can be estimated using the sample mean of the 10,000 replications of the jackknife standard error estimate, is essentially the mean of the third row of the results matrix. And that gives us something around 0.28, which again is quite close to the Monte Carlo approximation of the standard error of rho hat. As you can see, for this case, where our estimator is rho hat, the Pearson correlation between x1 and x2, the expectation or the sample mean of the jackknife estimators are really close to the true values.